These are the answers to homework 3G. First, the definitions that you're supposed to know, and then we'll move on to the questions. Question number 1, indicate which solvent, hexane or water, would be more suitable for dissolving each of the following. First one is NaCl, sodium chloride. This is an ionic compound, and ionic compounds and polar solutes are things that dissolve in polar solvents, so that would be water. The second one is HF. This is a polar molecular substance, and it has a hydrogen bonded to a fluorine, which means that that hydrogen becomes super positive and the fluorine can become super negative, and they can actually hydrogen bond with the O's and H's in water. So the polar HF would dissolve in polar water, and more specifically because it can hydrogen bond with water. Third compound, C8H18, is a hydrocarbon. Hydrocarbons are nonpolar and they will dissolve in nonpolar solvents, and the other solvent given, hexane, C6H14, is also nonpolar, and so hexane would be the better solvent for octane. Finally, Br2 is a nonpolar molecular substance. Any molecule made of only one element has to be nonpolar. There's no polar bonds in the molecule itself. And because that's nonpolar, it will dissolve in the nonpolar solvent hexane. Question number 2, in each pair, indicate which substance would be the most soluble in water. And if you have polar molecules, they're going to be highly soluble in water if they can hydrogen bond with water. So for the first pair, NH3 or PH3, NH3 has a very electronegative atom, and either NO or F in its formula, so that N in the NH3 is going to be able to hydrogen bond with water. PH3 does not have a very electronegative atom, so it's not going to be able to hydrogen bond with water, so NH3 would be the one you predict to be more soluble. In the second set, the first compound has a nitrogen in its formula, and that's one of the 3 most electronegative elements, NO or F. Those elements can always hydrogen bond with the H's in water, so CH3CN will be able to hydrogen bond with water. CH3CH3 has no NO or F, and it's a nonpolar substance, so therefore it's not going to be able to dissolve in water, and so CH3CN is the better choice. In the third one, we have a couple of organic molecules that both have oxygens in them. They both have 2 oxygens, and those electronegative oxygens would be capable of hydrogen bonding with the H's in water. So they each have 2 O's in their formulas that can hydrogen bond to water. However, the first compound has an H at the very end. That H is bonded to an O, and that H will become really positive, and it will be able to hydrogen bond with the O's in water. So the first molecule has 3 atoms, the O, and the H, which can each hydrogen bond with water. The second molecule only has the 2 O's, which will be able to hydrogen bond with water. None of the H's will, because they're bonded to carbons, not N's or F's. So CH3COOCH3 is polar, 2 atoms in its formula, it's O's that can hydrogen bond with water. But the CH3COOH is polar with 3 atoms in its formula, the final H and the 2 O's, that can hydrogen bond with water. That's why it'll be more soluble. In D, we had a pair of alcohols. These have both the O and the H at the very end of the molecules that can hydrogen bond with water. So it appears to be a tie. But this was a concept that was explained in the chapter. Before the OHs in each of those, you have a number of carbons and hydrogens. The first molecule is C2H5. The second one is C16H33. Hydrocarbons are nonpolar. So the C2H5OH has a small nonpolar component to its formula, but C16H33OH has a really large nonpolar component. So that means that the nonpolar components of each of those molecules will not be attracted to water, and therefore whichever molecule has the bigger nonpolar component will be less soluble in water. So the C2H5OH will be the one that's more soluble because the C16H33OH has a bigger nonpolar component, which does not attract to water, and the C2H5OH has the smaller nonpolar component, so it'll be able to dissolve in water better. Question number 3, a typical detergent is given and its formula is shown. Explain how this detergent can help remove oil and dirt from clothes in a washing machine. And this is going to relate to question 2D. A detergent has at the very right end of its formula SO4 minus and Na positive. That's a polar end. But the left side of the molecule, CH3, then CH2 taken 10 times, then CH2, that's a nonpolar component. So detergents, just like the alcohol we saw before is a molecule that has a polar component and a nonpolar component. A lot of times when a molecule like this is drawn, they show the polar component as a circle. In this case, it's a yellow circle. And they show the nonpolar component as a kinky tail, each of those kinks meaning a carbon atom in the long hydrocarbon chain. And the hydrocarbon chain end is the nonpolar part, and the circular end is the polar end. Well, if you have clothes that have oil on them and you put them in a washing machine, which is filled with water, and you add a detergent to it or soap, the polar ends of the soap molecules will attract to the water, but the nonpolar ends will attract to the nonpolar oil or grease. And as they attract around it, the nonpolar ends of the soap molecules will bond onto that oil or grease stain, and they'll form a micelle, a spherical type entity with all the nonpolar ends pointing in towards the oil stain and all the polar ends facing out with the water. So the polar ends attract the water molecules, and that allows the micelle to be suspended in the water in the washing machine. It lifts the stain off the clothes, the micelle suspends in the water, and then when you flush the water out of the washing machine, it pulls the stain with it. And it's the nonpolar end that's important. That secures the nonpolar oil or grease molecules in the center of the micelle, and that's how those actually clean clothes. If you ever hear of dry cleaning, they don't take clothes and put them in an oven to get them clean. Dry cleaning means you're cleaning them without water. So what they do is they take your clothes that have oil and grease on them, which are nonpolar substances, and they place them into a liquid that's nonpolar. So it's called dry cleaning because it's not with water. But the nonpolar liquid they put it in dissolves the oil and grease out of the clothes, and that's the way dry cleaning works. Question number 4. State the type of substances that are strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes produce lots of ions in solution. Those would be soluble ionic compounds and then strong acids. When we're talking about electrolytes, either strong, weak, or non, keep in mind this means things that will dissolve in water. So it's not a term you would use for something like sand or diamond. Those don't dissolve in water. But of the things that dissolve in water, if they form lots of ions in solution, they're called strong electrolytes, and those would be ionic compounds and strong acids. Weak electrolytes also dissolve in water, and when they dissolve in water, some of the molecules break apart into ions, and many don't. The only things that do this are weak acids. Those would be considered weak electrolytes. And then non-electrolytes would be anything that dissolves in water but does not produce ions. That would be all soluble polar molecular substances except acids. So that would be things like sugars and alcohols. Question number 5 says, state whether each of the following is a strong electrolyte, weak electrolyte, or non-electrolyte, and complete each of the equations. From the definitions above, well, KCl is an ionic compound. That's a strong electrolyte. So it completely dissociates in water. And so we would represent that by writing KCl solid yields K plus aqueous plus Cl minus aqueous. MgC2H3O2 taken twice is also an ionic compound, metal with nonmetal. Those are strong electrolytes. They dissolve in water, and when they do, they dissociate into ions, and the correct equation would have this dissociating into 1 magnesium positive 2 ion and 2 negative 1 acetate ions. The third compound is a sugar, sucrose, and sucrose will dissolve in water, but it will not break apart into ions. It's a molecular substance that dissolves in water because it hydrogen bonds, but it's not an acid, it's not an ionic compound, so it would be a non-electrolyte, and that means every single sugar molecule that dissolves in water stays a sugar molecule. They just float around independently with a shell of water molecules around them, and that's abbreviated by AQ, or represented by AQ actually. Next is HNO3. This is an acid, and you can tell acids are strong if they fit into one of these categories, either HCl, HBr, or HI, or they have at least 2 more O's and H's in their formula. And HNO3 has 2 more O's and H's in its formula, so that means it's a strong acid. And strong acids are strong electrolytes. They completely ionize, so every single HNO3 molecule would turn into a hydrogen ion aqueous plus a nitrate ion aqueous. The last substance here is H2SO3 sulfurous acid. This is an acid, dissolves in water, but it only has 1 more O than H, so it's not a strong acid. So this would be a weak acid. Weak acids ionize to a small extent, maybe 5% will break apart into ions, but 95% don't. And so the reaction we like to write is we like to show the reaction indicating the most prominent form of the dissolved substance. So 95% of the H2SO3s would exist in molecular form as shown here, where 5% of them would break apart into 2 hydrogen ions and a sulfite ion. And so the way we write the equation is how they exist as a majority case. The last question asks you to complete the following table of solute, whether it's water soluble or not, and then if it's water soluble, does it dissociate or ionize? And here are the different substances. CCl4, if you draw the Lewis structure, carbon has a steric number of 4, tetrahedron, 4 dipole moments in a tetrahedron are symmetrical, they cancel out. That's a nonpolar substance. If it's nonpolar, it will not dissolve in water. And if it doesn't dissolve in water, then we can't answer the question, does it ionize or dissociate in water? So not applicable. Next is a sugar. This has O's in its formula that can hydrogen bond with the H's in water. That's why sugar is soluble in water. But being a polar molecule, when it dissolves, it does not break into ions. It floats around in the dissolved state as intact molecules. So we say no dissociation or ionization. CH3OH is an alcohol. It has an O and H in the end of its formula that can hydrogen bond with water, making it soluble. But being another polar molecule that dissolves in water, it does not dissociate into ions. And so we'd say no dissociation or ionization. NABR is an ionic compound, and ionic compounds are soluble in water, and when they dissolve in water, they always dissociate into ions, and they dissociate into ions 100% of the time, so we would say a lot. HCl is an acid. Acids are soluble in water, and HCl is one of the strong acids we've learned. That means every single HCl molecule breaks apart into ions, so it dissociates a lot also. H2CO3 is an acid that will be soluble in water, but it only has one more O than H in its formula, so therefore that's a weak acid. Only small percent, 5% of them break apart into ions, 95% don't, so we would only say a little bit of them ionize.